Okay, the next talk is from Jacob Shen. We'll talk about star formation efficiency and UV variability in radiation idle simulations of redshift galaxies.
Testing. Hello everyone, I'm Xuejian Jacob Shen from MIT, and today I'm going to talk about the star formation efficiency and variability seen in the T-Sin zoom simulation. To provide a somewhat different perspective from the fire simulation. And as we have seen many times in previous talks today and yesterday, JWST is reviewing a surprisingly large abundance of UV bright galaxies, larger than redshift 10. But it's worth to note in this plot, the majority of the models that are compared to are effective models that are calibrated at lower redshift. Therefore, it's actually not surprising that they may not work in the regime that they are calibrated to. And an example is these effective models for an unresolved interstellar medium that's widely used in large volume cosmological simulations like Illustrious, CNG, EGO. And typically features some effective equation of state that aims to capture some unresolved feedback in an underlying multi-phase gas. Some grain particles are artificially created to carry momentum on long ranges. Some empirical star formation recipes are based on local scaling laws, and there are non-trivial level of calibration happening to these models. And therefore, the predicted power in extreme environments like extremely high redshift is not fully justified. And over the last decades, with the first example of fire model, people have been start thinking about doing this by resolving the multi-phase ISM and explicitly simulate the star formation and feedback process. And it's typically used in high-resolution simulations. And star formation can be modeled in resolved self-gravitating, gravitational unstable structures. It also involves resolving different multiple channels of feedback, like resolving individual supernova events, including early stellar feedback from stellar wings and different types of radiated feedback. And it's important that the input to these feedback models are directly from the physics of stars. In principle, at least for the feedback part, there is no apparent level of calibration. These models were initially proposed to explain the inefficiency of star formation we see in the universe. But there are phenomena that we see in these models that are interesting and that actually have implications to explain the UV luminosity functions at high redshift. And one of them is the burstiness of star formations in fire simulations. Another example is the existence of some feedback failure regime. The fraction of the gas that would be turning to stars during the life cycle of a GMC was saturated to order unity if the surface density of the environment is high enough. And this simply reflects that the gravity wing against all channels of feedback. And there's some conceptual difference between a feedback failure and a feedback free, but the critical surface density that this happens is quite similar, a couple thousand solar mass per parsec squared. And these phenomena have been seen way before these JWST observations. And in an empirical model that we did earlier last year, we show what kind of model variations is required to explain different level of the JWST constraints. And the direction you can go is to boost the median UV photon yield at given halo mass. You can do this by increase the star formation efficiency. You can also do this by increase the light to mass ratio with top-heavy IMF, for example. Another direction you can go is by boosting the UV variability. And this is simply because the halo mass function is always steeply decreasing towards the massive end. So if there is any scatter, the amount of low mass halos upscatter to brighter luminosities is always going to beat the amount of galaxies in massive halos downscatter to faint luminosities. And in this original work, we show that you need somewhat redshift-dependent, quite large level of variability to explain JWST. observations, but there are some follow-up studies that show if you have some negative halo mass dependence of the scatter in UV luminosity, then you might not need any redshift dependence. This is because the host halo of UV bright galaxies mass is actually decreasing towards higher redshift, so effectively you get higher sigma UV. And this level of UV variability and also the halo mass dependence have indeed been seen in Fire 2 simulation. Check out Jason's results. And as a side note, in a paper this year, we show that this is even easier to be achieved in a somewhat different cosmological model. This is an early dark energy model that was originally proposed to solve the Hubble tension. And the idea is that there could be some ultralight fields existing in the early universe, and it contributes to the energy density, it reduces the physical sound horizon at recombination, and therefore you would infer a somewhat larger value of H0 from CM. And all the physics parameters of early dark energy is completely fixed by a CMB observation. And lower redshift, the energy density dilutes very fast. It has no direct impact on cosmology. There is some indirect impact on structural formation that's by subtle changes in cosmological parameters. And it turns out that it would enhance the halo abundance at higher redshift preferentially, and at lower redshift it converges to lambda c. So it's kind of a free source of enhancing halo abundance at higher redshift. So we look at what that implies for the GWSC observation. It turns out that you need reasonable levels of UV variability of star formation efficiency to explain redshift 14 or even 16 results without any new physics on the barium side. And it also implies no tension with stellar mass density with cosmology, even if you consider the most extreme observation constraint. So this is another reason that why understanding star formation efficiency and variability is very important, because we can, if we narrow down the uncertainty on that side, we might be able to say something about cosmology and the solution to the Hubble tension. And now back to the main topic, the analysis I'm going to present are all based on the Thiessen-Loon simulation. It is a new suite of radiation hydro simulations that's going to be announced later this fall, winter. It's a joint effort with people either previously or now at MIT and people in AIP and MPA in Germany. The first part, the Thiessen, was a large volume radiation hydro simulation that was done in 2022. It simulates the reionization process in a 100 megaparsec box, and this is coupled to the illustrative TNG model. Well, in this new zoom-in project, it selects 14 galaxies at redshift 3 and resimulate them with the smuggle model that include all these resolved ISM physics that are crucial in capture, for example, the burst nearness of star formation. And just like as a technical overview, it involves generations of physics that has been implemented in the moving mesh called the Ripple. It includes the smuggle physics that includes many types of feedbacks and explicit star formation criteria. It also involves some additional early stellar feedback that is included purely empirically to give better agreement of the stellar mass halo mass ratio of redshift. May represent some distant physics in these simulations. It includes all the Thiessen physics or smuggle RT, basically on-the-fly radiation transfer using the moment-based approach that is implemented at Ripple RT. It traces 3 extreme UV bands, like Warner bands, far UV optical and IR bands. It has self-consistent non-equilibrium chemistry, hydrogen, helium, and H2. It includes dust formation, destruction, the coupling to the radiation. Another technical improvement is that you no longer require the assumption of a uniform UV background, because these galaxies are selected from the parent large volume radiation hydro simulation. You can fully utilize the knowledge about the radiation field on a larger scale by setting that as a boundary condition for the zoom-in. And just a kind of illustration of how that works. Here the white arrow shows the direction of the radiation flux. The white curve shows the boundary of the zoom-in region, and you can see that the image is color-coded by the ionizing photon density. You can see that there is a nearby source outside the zooming region, and this radiation is flowing into the zooming region. This is quite important for the low-mass galaxies selected by Thiessen zoom because their local environments are dominated by an outside-in realization. And it's crucial to capture the correct external radiative feedback on them. I should say that there will be an array of Thiessen zoom papers focused on many other different galaxy properties. Well, what I can present are mainly on the star formation. The first quantity I care about is the halo scale star formation efficiency. It is defined as the amount of baryon mass accreted by the halo that will be converted to stars. It's very useful for empirical galaxy modeling. Here I'm comparing the Thiessen zoom results with empirical models and predictions from Firebox and First Light. And overall, it's interesting that redshift around 6 is quite consistent with the redshift independent Firebox predictions. It shows no significant dependence on the physics variations, except some mild increase in the massive in the ROM without this additional early feedback. However, at higher redshift, it shows a mild increase beyond redshift 12, and it's actually kind of more aligned with the feedback free prediction. But it's worth to know that we are in no way getting close to the mass limits of the feedback free case. So we wouldn't be able to say like if in these simulations it is really feedback free. And as demonstrated later, we think that the enhanced star formation efficiencies were very different. Another type of star formation efficiency you can look at is the galaxy scale star formation efficiency, the relative position to the Kinnick-Schmidt relation. Here I'm showing the star formation ray surface density versus the neutral gas surface density, and compare Thiessen zoom results with the local observation. And it's very interesting that the majority of the Thiessen zoom galaxies at redshift 6, they follow the local Kinnick-Schmidt relation of main sequence galaxies. There was some signature of jumping onto the starburst stage in the most massive ones. And this indicates that the self-regulation of star formation is already there for redshift 6 in these simulations. And there is no apparent redshift evolution of the neutral gas diffusion if you go to redshift 12. You can try to relate this with the halo scale star formation efficiency. And basically, if it's not the diffusion time is smaller, then it indicates that the star forming gas and the neutral gas in the galaxy should be higher. And this is indeed what we see in the simulation, and kind of mimics the phase of realization. So here you're seeing the images of two galaxies with similar halo mass but different redshifts. And what's quite different is the amount of neutral gas applied in it. And similarly for the molecular gas. And it's even more apparent if you look at the larger scale distribution of ionizing density and H1 map. And it's worth to know if you use uniform UV background, you wouldn't get this because there will be a nonlinear transition of the IGM thermal state as soon as you activate the UV background. That's totally unphysical. And probably I wouldn't have enough time to cover things about the UV variability. Basically, we see variability star formation in Thiessen zoom galaxies and try to measure this. There's prominent halo mass dependence, but no redshift dependence. And if you compare that to, it's broadly consistent with other simulation predictions. And interestingly, the level of UV variability that we see in Thiessen zoom is quite consistent with what would be useful in explaining the UV luminosity function out to redshift 14 in an early dark energy. So there are the conclusions.
Thank you, Jacob. We have time for one question while the next speaker starts. The last speaker of the morning.
So thanks for the very nice talk. I think it's quite clever to use the UV background from Thiessen in the simulation, but when you do that, I don't know if you're propagating it through the M1 solver, but this is exactly where the M1 tends to fail, when you have flux coming out of the galaxy and radiation flux sort of going into it. So are you using a separate bin in order to model that, or ends up weakening the UVB in that case?
It is basic
M1, okay. Yeah, you might want to look at that.
There is some technical.
Thank you, Jacob, again.